Okay, so in this particular video, we have a basic position versus time graph here. So here, you notice the position time graph is given as a diagonal with the positive slope upward, a horizontal slope, and then a negative slope there. All right, so let's do it. So here are several parts that I've asked just to kind of teach you how to read these type of position graph to start. All right. So the first few part asks you to find the distance. It's good to know how to find the distance. Knowing the distance, that'll help you find average speed. And then I'll show you how to do average velocity later, because there is a difference between average speed and average velocity when objects turn around. And this graph indicates that the object does turn around. So if you notice here, there's a positive slope, aka the object's moving rightward, and then here's the slope is 0, which suggests that it's kind of just chilling out, resting, or motionless. And then the negative slope here would imply that it's moving backward. Okay, so I'll show you how to differentiate between average speed and average velocity. Okay, so let's do the first four parts here: A, B, C, and D. Part A asks you to find the distance between 0 to 2 seconds. So you just have to learn how to read these position time graph. In the vertical axis here, this is your position relative to time. The horizontal axis here is time, which is your independent variable. Okay. All right, so let's do it. So if you need to, I suggest you draw a number line out. Your number line, which is from your math days, is a horizontal line. However, that information is now flipped in the y-axis for a position versus time graph. So again, this number line here is now flipped vertically, so it's important that you interpret these data correctly. All right, so let's do it. Part A asks you to find from 0 to 2 seconds. So here I've drawn my black arrow here, my black dash arrow from 0 to 2 seconds. So you notice here in this particular graph, the initial position of the object is at 1 to start. It is not at the origin. So practice and then pay attention to the initial condition. So here I have 0 to 2 seconds. Well, it wants to know how far that the object, person, particle go. So all you have to do is really just connect, the dots. So here we have it going 2 to the right, which is 2 seconds. And then this red arrow indicates the distance traveled during that time. Okay. So in this case, if we count correctly, that'll just be a distance of 1, because as you notice here, if you go up from here and then if you go to the left, your position is now 2. Well, you were at 1 to start, and 2 seconds later you're now at 2. So that would be a difference of 1. So therefore you've traveled 1 meter. Okay. So here on my number line, I have an arrow here that indicates the starting position at 1, and then I have an arrow to the right to 2. So again, this horizontal arrow is this vertical red arrow in a graph. So it's important that you make this connection, otherwise you'll get a bunch of stuff wrong. Okay, so the distance horizontally here is from 1 to 2, which is just a distance of 1, which is what the graph is indicating. All right, so the answer for that is just 1. Okay, all right, let's do the next one. So hopefully as you practice, you catch on how to look at these graphs. Okay, it wants us to find the distance from 0 to 4 seconds. So I'll go ahead and draw my dash line here from 0 seconds to 4 seconds. So again, on the horizontal axis, which is time, I'll just go to 4. And I've drawn that line there because that's where the position graph starts. So that's 4 seconds. And I'll just draw a red arrow all the way to where it touches the actual graph itself. And then from there, if you look to the left of where this point is, you are now at a position of 3. Well, you started at 1, and then 4 seconds later, you are now at a position of 3. So on the number line, it'll look like this: 1, and then you've taken 2 ticks to the right. In this case, 2 meters. So therefore, from 1 to 3 is just 2 meters, which is consistent with what the graph is portraying. Okay, so the answer for that is just 2 meters. All right, and then let's go from 0 to 6. All right, let's do it. From 0 to 6. Okay, so but you notice here from 0 to 6 you have 2 types of lines. One, during the first 4 seconds you have a positive diagonal, and then from 4 to 6 seconds you have a flat horizontal line. So as you practice, this horizontal line is pretty whack. It's just pretty easy to do. All right, so I will go ahead from 0 to 6, but from 0 to 6 I can just draw my arrow all the way to 6 seconds, and then I can just draw an arrow up there, and that arrow up is also a distance of 2, because well, I start at 1 and I went to 6 seconds. I went all the way up to where it touches the graph, and then if I go all the way to the left where the numbers are on the vertical axis, that is a position of 3. So therefore the distance here is also 2. Okay, so while the time has increased, the answer is the same for this one compared to part B. Is because from 4 to 6 seconds the object didn't go anywhere. So it got to a position of 3 at 4 seconds, and then it just kind of stood there for 2 more seconds, which makes sense. Because if you kind of trace your time up from 4.5 all the way up to the graph, and you look left, you're still at a position of 3. If you go to 5 seconds and you go all the way up to where it touches the graph and you look left, you're still at the same position. Well, for you to stay at the same position, it suggests that you haven't moved anywhere. So notice here, for an x of t graph, anytime you see a flat horizontal line, that just tells you that the object is motionless during that time. So while time is ticking, the object or the person didn't move anywhere. So there's no distance to be accounted for. All right. So the answer is the same as part B and C. All right. So let's do D. Okay. So D wants us to go all the way to 9 seconds. Okay. But again, you notice here for the graph, the positive slope here suggests that the object is moving towards the right, because the slope of an xt graph tells you the direction of motion. Here, the slope is flat, tells you that it doesn't move. Here, the slope is a negative slope. That suggests that the object has turned around and is moving in the opposite direction. All right, so we'll just take it one segment at a time. From 0 to 9, I notice there are 3 different segments. There's a positive slope, there's a 0 slope, and then there's a negative slope. So I'm going to go from 0, okay, to 6, but we already know from 0 to 6, which is 2. So really, in this case, I just have to take it from 6 to 9. Okay, and I already know the answer from 0 to 6. So now, because it wants me to go from 0 to 9, I can just add the extra 3 seconds, which is from 6 to 9. Well, from 6 to 9, this is where my black arrow is. That represents the amount of time, which is from 6 to 9. And then from at that location, if I draw an arrow all the way down here, where 9 seconds represents, and I go all the way across to my vertical axis, that would be at the origin, which would suggest that the object's position is now 0. Okay, so you notice here there's red arrows pointing down, which suggests that the object has gone backward. So on the number line, I have drawn from 3 to 0, because at 6 seconds, if you go across, the object starts at 3, but then by the time it gets to 9 seconds, if you go across, it has gone to 0. Well, on the number line, to go from 3 to 0, you must have walked leftward 3 meters. All right, so that's that. So, but it asks for distance. So to find distance, we just simply sum up the distance covered. So from 0, right, from 0 to 6 seconds, which we did in the previous problem, that's just 2. And then from 6 to 9 seconds, it has traveled a distance of 3. Because distance is a scalar quantity, you don't need to add a negative sign. So it would just be 2 plus 3, which is 5. All right, let's do part E. Part E asks you to find the average speed for 0 to 1 second. Well, to do average speed, we simply just apply the average speed function, which is equal to distance over time. Well, let's find the distance real quick from 0 to 1 second. So learn to read graph carefully. Here are my little 2 arrows again. So if you do this as you practice, it hopefully will minimize the amount of mistakes you make. Okay, from 0 to 1 second, that's where my black arrow is. That's my time. And then here's my red arrow that represents my distance. Again, distance in this case would be 0.5 because I start at 1. 1 second later, my position is at 1.5, so I've only traveled half a meter. So therefore, simply plug that in. Distance is 0.5, and then time is 1 second because the interval is dictated for you there. So 0.5 divided by 1 is just 0.5 meters per second. And average speed is a scalar, so you don't need to include any sort of direction. All right, let's do part F. Part F asks us to go from 1 to 2. Okay, so again, I'm just gonna draw my time arrow from 1 to 2, which looks like this on my screen that just came up. I'm gonna do that. There you go. That's from 1 to 2. Again, here's 1 second on the. I'm gonna go up there where it touches the graph. I'm gonna go over to 2 seconds, and then I'm gonna trace all the way up to where it touches the graph again. So if you are able to draw these little 2 arrows and then count correctly, here it starts at 1.5 and then the arrow goes up to 2, so you've traveled only a half a meter. So therefore, the answer for this one is just 0.5 meter as well. The distance is 0.5 divided by 1, which is 0.5, which makes sense. Now I want to point out the answer for these last two parts is the same because the slope of an xt graph, okay, this is your slope, tells you how fast the object is moving. But if you're looking at the slope properly, this slope is a constant slope, which means at any point, if you take the average, it will be the same. Okay, so whether it asks you from 0 to 1, the answer is 0.5. If it asks you, let's say, from 1 to 2, like I just did, that's also 0.5 because the slope has not changed. What if it asks you from 2 to 3 seconds? Well, if you do this and you find the slope will also be the same. So really, they're all the same answer. So the average speed is really the same from 0 all the way up, to 4 seconds. Okay, it's 4 seconds there. All right, let's do average speed from 0 to 9. From 0 to 9, it's a bit more work, so let's do it. Again, average speed is distance over time. We have to find the total distance. So if you pay attention in the previous part in terms of finding distance, I noticed here in the graph, it went to the right and then it kind of chills. So I'm just going to go from 0 to 6 seconds. 0 to 6 seconds suggests that the object has gone a distance of 2. Again, be careful with numbers. It started at 1, it ends at 3. So this red arrow here is only a length of 2 meters. Okay, but that only takes me to 6 seconds. But the question asks from 0 to 9. So I now have to go from 6 to 9 and find out how far it has gone. So similar to the previous strategy in finding distance, from 6 to 9 seconds, I know it has gone left a distance of 3. Well, it started at 3, and then by the time it gets to 9 seconds, you go across on your vertical number line, that's at the origin. So 3 to 0 is 3. So therefore, the total distance here is 5, because 2 plus 3 is 5. And then 5 divided by 9 will give you a value of 0.556. Okay? So that's the answer. Again, average speed is a scalar, so you don't need to include any sort of direction. So I hope you understand how to find distance simply just by drawing these vertical lines up and down and adding all of them, because distance is a scalar, so we just add all of our steps. All right? Let's do average velocity. Here's part H. So part H asks us to find the average velocity from 0 to 8 seconds. Well, from 0 to 8 seconds, I know that the first part, okay, is from 0 to 4 seconds, so I'll chunk it up again here. And then it has gone a distance of 2, or a displacement of 2. So now that it asks for average velocity, which is the vector, you have to be careful with when to include direction and when not to. All right, so on my number line, I have it here. During the first 4 seconds, it has covered a distance of 2, or a displacement of 2 to the right, because it started at position 1, it's now at 3, so it has displaced itself 2 meters forward, aka to the right of the screen. All right, but then I know that from 4 to 6 seconds, it has not moved anywhere. It's motionless because the slope here is 0, and if the slope here is 0, it suggests that your average speed is 0, which implies that you're not moving. So that doesn't count for anything except for time. And then now I got to take it from 6 to 8 seconds. So again, so my little black arrow here represents from 6 to 8 seconds. I'm going to go down and touch the graph where it is at 8. And I notice here it moved leftward because this arrow is drawn downward, a displacement of -2. Well, if I go all the way across to my number line again, I'm back at 1. Okay, so if you think about it, you went 2 steps to the right, but then you took 2 steps backward, which puts you exactly where you started, which is at an initial position of 1. So what's your displacement? Well, you started at 1, you went 2 to the right, and you took 2 steps backward, you end up at 1. So really, in a physics sense, you haven't displaced yourself. There's no change in position, okay? So your displacement is just 0. You're back to where you started. Therefore, 0 divided by 8 seconds is just 0, because your answer here is 0 meters per second. You don't need to include any sort of directions, okay? That'd be kind of redundant, all right, or unnecessary, because there's the average is 0. All right, so let's do part I. To do part I, it wants us to go from 0 to 9. Okay, so watch. I want to take it from 0 to 4 again. I know from 0 to 4 that red arrow is 2 because it starts at 1, it finished at 3 in terms of position. So here in my number line, I went from 1 to 3. Again, during the 4 to 6 seconds, it's motionless, so I don't count anything. And then from 6 to 9, okay, 6 to 9, you went backward. Okay, how do I know you went backward? Well, because this is a negative slope. It suggests that your velocity is negative. Therefore, from here all the way back down 9, it touches the graph, and I go to 0. So it has gone leftward. How do I know when leftward? Because this arrow is drawn downward. Okay, all right. So there's my arrow on my number line. From 3, it went all the way back to 0. So what's my displacement? Well, I start at 1. By the time I'm done with all this movement, I'm at 0. Well, if you just put, a pen or a marker on the screen and you go from 1 to end up at 0, you must have displaced yourself 1 meter to the left. Okay, so that's that. So it's -1 because you start at 1, you end at 0. So if you draw an arrow, that arrow must be pointing leftward, which suggests that it's negative. And how many meters? 1 meter, and then over 9 seconds. So your value for average velocity would be -1.111 meters per second. All right, the negative sign in this case is appropriate because average velocity is a vector. Again, unless a question asks you for the magnitude, then you can leave the direction out. All right, other than that, that's how you do that one mathematically. But hopefully you can watch this next slide. This particular slide will teach you how to find average velocity, okay? Average velocity, average velocity, average velocity, not average speed, okay? To find average velocity is pretty easy if you know how to do this little skill. Well, here it says from 0 to 8, so I would just connect, the graph from 0 to 8. But I notice here my purple line connected from 0 second all the way to 8 seconds. So if you just kind of use common sense here, what is the slope? Well, it's a flat line. There is no slope, okay? A horizontal line has no slope. Well, if slope is equal to 0, it suggests that your average velocity is 0 because there is no rise. If there's no rise, it doesn't matter what your run is, okay? Because slope is rise over run. Where if there's no rise, because this arrow is perfectly flat, there's no vertical movement. If there's no vertical movement, your rise is 0. Your run in this case is 8 seconds, but 0 divided by 8 is just 0. So the slope tells you what your average velocity is, which in this case is just 0. Let's do part I using the same strategy. Again, part I asks you from 0 to 9 seconds, so I'm just going to connect, I'm just going to draw a straight line on this graph that connects 1 to 9. Okay, see where that purple arrow is. I went back to 0 second. I'm going to draw a straight line that connects from 0 to 9. Well, from 0 to 9, I can make it into a right triangle. So my little purple dashed line there, that's how much time has gone by. Again, the horizontal axis is your time. Okay, the horizontal axis is your time as indicated by the graph. That's 9 seconds. And then the vertical axis is your displacement. In this case, you notice there the arrow is pointing down. So if you think about it, there's 9 seconds, and then if you count on the graph correctly, this is -1. So this is 1 on the screen, this is 0, so you went down -1 meters. Well, slope is just rise over run. So in this case, my delta x here is my vertical axis, which is my rise, which is -1. My t, which is my horizontal axis, which is 9 seconds. So if I plug that stuff in, I also get the value of -1.11 meters per second. Okay, so for average velocity, you can apply this strategy. It works all the time because velocity depends on displacement, and displacement is independent of path taken. That just tells you it doesn't care for what you do between start to finish. All that it cares about is your starting point and your ending point. Hence, it allows us to just draw a straight line from start to finish and just find that slope. Okay, so that's it. So here I put on my screen, only do this for average velocity because it depends on displacement, and displacement does not care for what you do in between start to finish. It only cares from where you start to where you finish. So therefore, just connect the dots. Draw a straight line and find that slope, and that slope is your average velocity. Okay, I hope that helps. Stay nerdy.